Alright, so we're going to continue with these examples for these trigonometric integrals. Now, the next example that we're going to be doing here is going to be example B, where we're going to have the integral for tangent to the fifth of x multiplied by secant cubed x dx. Now again, some of the initial methods are to, again, list out all the methods that we can use, but one of the items that I want to direct your attention to at this particular time is that we can use any one of our Pythagorean identities to make any substitutions that we'd like. And I also want to establish that if we wanted to make a u substitution, or say we wanted to proceed by parts, then we would need to look at some of the derivatives for the substitutions that we're going to be making. Now, the derivatives I'm listing here are just for secant and tangent, because again, secant and tangent are what we're observing here. Now, one of the first items that catches my eye here is that we do have tangent and we do have secant, but more importantly we have secant. If I take the derivative for secant, then that means that I'm going to be looking at secant x tangent of x, and that's kind of where I want to be at. But in order to do that, I need some sort of tangent times the secant of x. So what I'm going to do really quickly here is I'm going to separate this tangent squared multiplied by tangent of x, and therefore I have 5 tangents multiplying one another, and I'm going to do I'm going to keep my secants not necessarily the same, but I'm going to split them up in just a little bit. Alright, so this is going to be secant of x multiplied by secant squared of x, and this is all dx. Alright, nice. It's looking real good. Now, what I want to do at this point in time is I want to use this tangent squared of x. Tangent squared of x has a really nice substitution. Tangent squared of x is really secant squared of x minus 1, using our substitution, and that's squared. And now we're left with tangent of x, secant of x, multiplied by secant squared of x dx. And what I want to do at this point in time is I want to stop and I actually want to make a substitution here. I want to go through and I want to say, hey, I think I see something here that's going to be really nice. If u is equal to the secant of x, then when I take this derivative, the derivative of secant of x is just going to be tangent of x multiplied by secant of x. Therefore, when I go through and make my integration, this will now be u squared minus 1 quantity squared, tangent of x multiplied by secant of x, this was all dx. Whoops, different colors, that's okay. Alright, which means that's going to be substituted in there, and that means that this is just going to be u squared du. Alright, and again, I was looking at this piece here, this du. du is this piece right here that I'm highlighting. Alright, so that was all tangent of x times secant of x dx, tangent of x times secant dx, we see it there, and then our u was equal to secant of x, therefore this became our u substitution, along with this piece here. Now, all I have to do at this point in time is go through some algebra work, and going through some algebra work here, let's go ahead and expand and then distribute that u squared into that polynomial. Then u squared, that's going to be u to the 4th, multiplied by another u squared, that's going to be u to the 6th, minus 2 times a u value. Now it's going to be 2 times u squared, but then multiplied by u squared again. That's going to be u to the 4th. And then this is finally going to be plus 1, but then multiplied by u squared. It's just going to give me u squared. And now this just turns into a really quick integration for a polynomial. So the integration for the polynomial here is going to be 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u to the 3rd. And then we need a plus c because, again, we're working with this indefinite integral. Now that we have this, we can go back and we can now make our resubstitutions. We're not solving for u. U was the substitution that we made for secant of x, so that's 1/7 times secant of x to the power of 7 minus 2/5 multiplied by secant of x raised to the power of 5 plus 1/3 multiplied by secant of x to the power of 3 plus c. And here's our final answer. Yes, I know, it's pretty intense. But again, at the end of the day, we have to rely on our trig substitutions and on our trigonometric derivatives in order for us to arrive at this conclusion. All right, awesome. Now, I also want to work on one more example before we end this particular section. And this last example that I want to work on is going to be part C. So part C is going to be the integral of x multiplied by tangent squared x dx. Perfect. Now, again, as I'm looking at this, there might be different ways to approach this and different methods that we can try. Now, one of the methods that I want to look at here is because I see a tan squared, I want to really quickly go back to that Pythagorean identity. That Pythagorean identity that we used for tangent squared is that when we're looking at secant squared x, this must be equal to tangent squared x plus 1. Now for us, making this substitution here, this is going to be x multiplied by secant squared of x minus 1, and this is all dx. Now, making the distribution for the x onto that secant squared x minus 1, I'm also going to go ahead and separate this integral. Alright, and I need a dx here. There we go, minus the integral of x dx. Now, looking at this integral, the left-hand side, or the leftmost term, and I'm going to highlight that term really quickly. This term here needs to be performed by integration by parts. So I'm going to go through with integration by parts really quickly in order to make that work. So here we go. We're going to make our u is equal to x. Therefore du is going to be equal to dx. dv is secant squared x dx. And when we integrate this, or when we find the antiderivative, that means that v must be equal to tangent of x. Now, using our rules for by parts, we're going to do u times v minus the integral of v du. And that's going to be u times v, so that's x times tangent of x, minus the integral of v du. So it's going to be the integral of tangent of x dx. And then here we still have minus the integral of x dx. Now minus the integral of x dx, that just pretty direct integral, 1/2 x squared. And then we're going to need a constant for all of these integrals. So as you can see here, this is a really nice looking evaluation at this point in time. And the last piece of the puzzle is going to make sure that we finish evaluating that we finish evaluating this integral of tangent of x. Now, if you recall, the integral of tangent of x was a really nice integral that we've already proved in the class, and we proved this around week 1, week 2. Oops. doesn't need that integral. So it's going to be minus, and it's going to be minus the natural log of the absolute value of secant of x, and then we have minus 1/2 x squared plus c. And I'm going to go through and I'm going to write the integral that we used. The integral that we used was that the integral of tangent of x dx is equal to, let's say, negative natural log, or actually positive, sorry, positive natural log of secant of x plus c, or we could have chosen to say it's the negative natural log of the absolute value of cosine of x. Whichever one, it's still the same answer. And that's my little asterisk. All right? And so this is our final answer. This is the answer that we want to see at the end of the day, or that I want to see at the end of the day. All right? So if you have any questions, again, please feel free to contact me, but this is now us wrapping up section 7.2, where we were working with trigonometric integrals.